Hello everyone, and welcome back to a new video in programming the finite element method using MATLAB. In this video, we are going to be talking about something called FEM Bar Spring. And as the name suggests, it's going to be basically a finite element object that is a bar, meaning it has two nodes and 12 degrees of freedom, and that is a spring. It could be a rotational spring, it could be a linear spring. It is a spring element that connects node 1, for example, with node 2. So we need to program this because we need to program something called a FEM bar spring and a FEM bar beam to achieve our FEM objects for this program. Now, if you are new to this video series, please notice that it's part of a finite element method playlist linked at the top right. And if you're a programmer who is only interested in programming, there is another playlist also linked on the top right. As per usual, my dear channel members have access to the entire code. You can join them if you want, but if you don't want to join them and you're still worried about getting the code, don't worry, because every single line of code will be written in front of you. So if you write along, you're going to be just fine. So with that being said, let's take a look at the FEM bar spring and let's sit back, relax, and enjoy the show. I usually program the STI controller once an object has been accomplished, but this time I want to change my style a little bit. I will postpone programming the STI controller with a FEM node guy because I want to focus on the second element, which is the FEM bar, for reasons that will come apparent like 3 videos in the future, or 2 videos. I don't know how long I need to get the FEM supports. But for now, let's dive into it. So I still haven't included an STI controller algorithm that defines things for me, because if you remember, I had certain regions. For example, I had a region for node definition and support definition and so on. And the controller usually takes care of getting the IDs, but that's something I will leave for later. For now, let's focus on the FEM bar spring. I'll keep this open, but I'll open another one. And this one I will call Control Save, and I'll call FEM bar spring. Now I need a lot of things there. Because this is a finite element method object, it would need all the shenanigans of the finite element method, such as stiffness matrix and whatnot. So we're going to program this right away. So let's dive into it. First of all, since I have a finite element, I would need to class div it first. So FEM bar spring. I'm going to end the class div. Now I could use inheritance, and I could define me a FEM base and then inherit from it. However, I don't want to use inheritance. I want to keep it simple for our dear regular viewers, as most of them are of civil engineering background. I don't want to start with inheritance and polymorphism. And by the way, I'm gonna inherit from the class handle. This is the only inheritance I do because this allows you to keep track of the changes of a class, but I'm not gonna go deep into the inheritance stuff. I just want to keep it a simple tree. And my FEM node also I forgot, so I will just let it inherit from the class handle. And let's continue. First of all, this is a FEM object that has a stiffness matrix. So what do we need for this? Well, the first thing is I might need a constant here. So properties, and I will put here constants, and I'm going to put here DOF equals 6 because the degrees of freedom of a node is actually 6. Let's put it as a constant and continue. Now here, let's go to the real properties, okay? And here I am going to give a lot of properties. I would need, of course, the local stiffness matrix. Because, local stiffness matrix. And here also, I will need something called local displacement matrix. This is the displacements of the nodes in the local axis sets. I would also need the local force matrix. I would need those two dudes because I may be interested in finding the local forces of an element for post-processing purposes. Because you know that local forces equals local K multiplied by local displacement, X. So I need to have them, and I need to calculate them. Then I also need the transformation matrix, because of the finite element, K global is TKT or something, or I think 3 transpose. Then I need here the global elemental stiffness matrix and the global structural stiffness matrix. The global elemental stiffness matrix is a 12 by 12 matrix that is in the global sense, and the structural stiffness matrix is a, maybe I don't need that, is a huge matrix where the 12 by 12 is distributed. This might be a memory drain source, a memory sink, I guess. I might rethink it for later. Let's keep it for now like this. Of course, here finally, I would need something called local equivalent nodal force matrix, because on the finite element method, if we have distributed loads, we can calculate the local equivalent nodal forces. Now, those are generalistic terms for any finite element. Now, for spring, I may not necessarily need all of those. Maybe I need just some of them. For example, the local equivalent nodal force won't be an issue because there aren't any distributed loads on a spring. However, I want to stay consistent, so I'm going to keep those things as my little finite element properties. I'm going to put here even a region and say FEM properties, okay? Just to kind of show that those come with any finite element that I have, even if it's a shell. Okay, now, what else do I need? I think that's it for now. There will be general purpose methods here. So here there will be general purpose methods, and those methods will be filled in later. Here we're going to calculate local stiffness matrix and so on, and maybe calculate other matrices before some post-processing, but this is for later. I think we're not finished with our properties because we still need to give the node 1 and node 2 and other things that define what the spring is that it is connecting. I'm also thinking loud now, since this is a bar, I think I need more things here. Let me put here something called general FEM bar stuff. Here, let me put here FEM base properties. I mean, those FEM base properties are properties that any finite element object needs. Now, general FEM bar stuff are the things that any bar element needs, which is basically an ID, okay? It also needs the FEM node 1, starting FEM node, and the FEM node 2, and it also needs its directions, Vx, Vy, and Vz. Yeah, I think I need them. So I'll put here Vx, this is the direction local x, Vy, direction local y, Vz, direction local z. And maybe it doesn't hurt if I get the corresponding str line, because I could take some stuff out of it. I don't know, maybe I should keep it. You know what? Let's overkill it for now and then later remove stuff that we don't need. So here I also need the section, I need the material. Why do I decide that I need those things? I'm thinking now, how did I decide those things? I'm thinking, what do I need to calculate the global elemental stiffness matrix? And I thought, hey, I need the nodes first of all, so I know exactly where the elements are. I need those dudes to find the transformation matrix. I need those dudes to calculate the stiffness matrix. And this may be to know exactly which line corresponds to this entire brouhaha. So that's the reason why I thought I might need those things. Let's also add length for good measure. And yeah, I think some of them are kind of not required, because I mean, section, I don't really need it because I could fish it out from the corresponding str line. I could just say corresponding str line dot section. I'm not really sure if I need those two things and those three things, because they could be taken out of the corresponding str line. I'm not really sure. I'll keep them for now. I think those 5 are really an overkill. I could just say corresponding str line dot vx to fish that out, but I will keep it for now. For the length, no, that's something I need. Because yes, you could have a corresponding str line that is 10 meters long, but if it is intersected by another line, then 2 FEM bars would generate. Each one of those will have its own length. So the length is definitely something that we need to keep alone. So let me just put this up to kind of denote that here. Let's put here a comment and say Vx, Vy, Vz, section, and material could be taken from corresponding str line, but I'm not going to do that anyway. Just a link, just a hint for me for the future that I could have simplified my programming. Okay, what else do I need here? Let me think. I don't think I need anything, to be honest. Fine. Now this is the general FEM bar stuff. Let's put here now specific spring stuff. Now, those things are for any line. Those things are specific for the spring. Those things are for the FEM base. Those things are the FEM bar or FEM line. And those things are for the spring. You can see the inheritance here. I could make a base. Wait, what's the problem here? Constant. I could make a base class that has those things, and then derive a class from it that has those things, and then derive a class from it for the FEM bar, that has those things, and then derive a class for the spring that has those things. But I'm not going to use inheritance. I will try to keep my programming as simple as possible for my target audience. If you are a programmer who is really into programming, I do have a Udemy course where I do the same thing in C#, which is actually more complicated, and there will be inheritance and polymorphism and whatnot. But for now, I'm not going to do that. I'm just going to go specific spring stuff. So let's add our specific spring stuff. Now a spring, well, the only thing that kind of makes a spring special is its spring constants. So here, I'm going to add me a KUX, KUY, KUZ, and you know the drill, KRX, KRY, and KRZ. I'm not going to make a start and end because I will assume the start and end have the same spring stiffnesses. And those are the things that the spring needs. Now in the methods of what the spring can do, this is going to be filled with tons of code, but that's going to come for later. For now, I need the only one thing, which is basically a constructor. So function object equals FEM bar spring. And let's take a look what I need to construct this FEM bar for me. I think I would need an ID here. And I would need the first FEM node, the second FEM node, and I would need the length for this one. Not really sure. I could find the length from FEM node 1 and FEM node 2 because I could find the norm of it. Whatever. Let's just get the length here. Vx, I think I'm overkilling it here. Because if I have FEM node 1 and FEM node 2, I could find length Vx, Vy, and Vz myself. But well, let's just roll with it, okay? Here, I think that's the only thing I need for now. Let's just basically do that. So here, object.id equals id, object.fem fem node 1 equals fem node 1, object.fem node 2 equals fem node 2, object.length equals the length, and object.vx equals vx, object.vy equals vy, and object.vz equals vz. I know I haven't initialized everything, and I will initialize those things in due time. Otherwise, I would risk losing you because I'm trying my best to keep you on track with me. If I start initializing things that come ages later, then I would run the risk into losing you. So I will not try to run the risk here. In the end here, I would need a toString function, or a reporting function, as I like to call it. So toString object, and now I'm gonna report the object. I'm gonna go to the str line and copy me some of its reporting system, not everything. So I'll go down here. This is the reporting system of the str line. I think I'm only gonna take the node thing. That's the only thing I'm gonna take. So I'm gonna copy this, go to FEM Bar Spring here, paste it, and I'm not gonna report anything like material and whatnot. I'm just gonna leave this. Just gonna report the line. Now it's not a line, it's a FEM Bar Spring. So I'm gonna report FEM Bar Spring. And it has an ID from FEM node 1 to FEM node 2. And this is called FEM node 1. And that's called FEM node 2. And I think we have arrived at another milestone, I guess. And we need to do a quick check if it works or not. I hope it works because I want to stop the video here. So let's test again. Let's put FEM bar spring 1 equals FEM bar spring. I want to remind you that the user shall never be able to define a FEM bar like this. It should be done via the controller, and even the user should not be able to do that. So let's put here FEM bar spring. What does it want from me? It wants 2 FEM nodes, right? I don't have that. Let's make another FEM node. So this is 0 now, and that's 1, 1, 2. Now let's try our best. So it's ID Okay, why isn't it showing? Oh, it's caps. Why is it caps letter? Should be small. FEM Bar Spring. Yeah, I think I missed it. So now it should appear. Let's try it again. FEM Bar. Yeah, there we go. Now it appears. ID, FEM node 1, FEM node 2, length. I should calculate it, but I'm just going to put 3 now. VX, I'm going to put 100, just dummy stuff. 100, although it's impossible, and 100 because it's physical, although it's physically impossible. Just want to see if somehow it works. So I just want to test here. And let's push F5 and hope it works. And it doesn't work. Fantastic. The ID is not missing. Okay, I must provide a number for myself. So ID is -1. Let's run again. FEM node 2 is unknown. Yeah, because I did it twice. So let's put this FEM node. See, because I'm in a rush now, I'm making mistakes. But now it's working, I guess. So let's double check. FEM node this one, FEM node that one, and then from FEM node 1 to -1 to FEM node 0. And yeah, I think we're doing great so far. So yeah, I think we have reached another milestone. We have programmed what the FEM Bar Spring is. There is a lot more to be expanded on this class because there will be calculations for the stiffness matrix and the transformation matrix, and all those juicy matrices are gonna be calculated here. But that's, of course, an issue for a later me to think about. The current me will have to end this video here and go finish an errand that has popped up from nowhere. So a wild errand has appeared. Anyway, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a hastily sized shout out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.